battery went dead, and that caused the program
switching gears.
crash. Okay, but as you look at this here, this is a 512 gigabyte hard drive, fits onto the motherboard, and the price of that is quite expensive. If you multiply that by 4.2, right there, that's pretty expensive. The system I just put together, I put 256 in, and it cost me about 800 ringgits for the hard drive.
From the hardware standpoint, so I'm going to
but it did make it much.
I
mean, the system boots super fast.
So let me.
Right there. This has got that type of drive in it too.
Talk about now this.
A lot of the newer laptops are going for that. If you look at a lot of the newer laptops are using solid state drives. So going back to this discussion here, I believe the flash memory will replace part of the hard drive as mass storage medium. That is not. It's believed will. It's already done right there. So we are now seeing flash memory replace hard drive. Again, the same thing with your phone.
When we look at the number
if you've got a phone with 32 gig of RAM or 16 gig of storage on it, not the RAM. The RAM is different. Most phones have got between 1 and 3 gig of RAM out there.
So when we look at
but your phone also has in it, say, 8 gig, 16 gig, 32 gig, or 64 gig, and I think some of the Apples come with 128 gig of RAM, or not RAM, but storage. That's flash memory as well, right there. So you would not have cell phones, smartphones, if it wasn't for solid state memory. Solid state memory has made the smartphone possible. And trust me, I actually had one of the old Palm Pilots that had a
there's an address for every
1 gigabyte hard drive inside of something you carried in your pocket. It had a physical hard drive in it. You know, this was before the solid state memory became feasible. So, this is widely used as a way to upgrade the BIOS. Before you can use flash memory on the BIOS, the old original IBM PC motherboards that I out there, you know, this is the old IBM PC, you know, we're talking 1980, yeah, 1982. Actually had little header strips here where you would tell it, you put jumpers on it. You put a jumper on this one, a jumper on this one. You tell it how many hard drives you had, how many floppy drives you had, how much memory you had. You had to put jumpers on this for the BIOS to look at that. You couldn't program that into a BIOS screen. When you boot up your computer and you hit the delete button, you know, to bring up the BIOS screen, what you're doing is you're writing to the flash memory on the motherboard that set up the configuration.
And you can typically tell how it's organized.
Before flash memory, you had to have jumpers on the motherboard to do all that, set all those things there. The jumpers have all but disappeared. I think the only jumper on my motherboard is there's one to clear the CMOS.
Typically, a memory chip will contain 2 to the N location.
So flash memory, and actually a lot of them don't use flash memory. They use non-volatile. They have a battery backup on some of them too. Still,
number of locations.
So what they're saying is that the programming erase cycle for flash.
So an example of that would be
for flash is about 100,000. That's much higher today.
Look at a device
because if it was that low, you could not use flash your thumb drives. So that's 100,000 times you can erase and reprogram, When you talk about using it for a computer hard drive, that's not very many read-write cycles. That's not a lot. Every time you move a file, you're probably rewriting the same location 3-4 times.
Pin out.
So the last one in this list is the mask. The mask is what you use once you have a system firmly in place and you're not going to change it.
What we're going to see here is that we've got address lines A0
the process is very expensive,
around to A10.
Very costly. But so you use it when the volume is high and you're certain that the contents will not change.
There will be a question on the final exam where I give you a picture like this.
So
ask you the memory
those are the key times. I have never worked on a project where we've gone to a full mask. I've worked on projects where we've gone to the prom, but not to the full mask. Because most of the projects I've always worked with, we might build 10,000 of them and we're done. Because a lot of what I worked on was either military or for small companies. So we weren't making millions and millions. The company, I'll use an American company as an example, General Motors. Everyone's heard of General Motors. They make Chevrolets and Chrysler or Chevrolet Buicks. But General Motors is a big company. They sell cars here under the name Chevrolet. They used to sell Opals here, which is a General Motors product. That there. But General Motors makes how many millions and millions of cars a year? And if you can save 10 cents per car, you've saved a lot of money. That there. You see, that's the key there is the volume. The cost difference between a prom and a mask is probably, I'm just throwing these numbers out. A prom might cost, say, 5 ringgit RM, and a mask ROM might cost 3 ringgits. So there's a 2 ringgit difference between the two parts. But it may cost you 10,000 ringgits to generate the mask. So you have to make enough of it. You have to have a large enough volume to justify the process of making the first one.
Things we have to look at.
Back in my days, the joke was that the first 5 chips cost you $10,000 a piece, and the 6th chip you bought cost you 50 cents.
Most of the students
there. Those first 5 chips would come up to about $50,000 for the initial prototypes that they send you. They would always give 5 prototypes there. So unless you're making a lot of parts, you're not going to go to the full mask there. So in the same token, because of the high cost of EEPROMs back then, we would never go into production with EEPROMs. But the one-time programmables, we would program them in-house. So if we were going to, that would just be part of our manufacturing costs there. So if we were going to be able to say 5,000 units of something, we would buy 5,000 proms and we would program them before we put them on the production line there. So you would program them and then they would go into production there. So EEPROMs were just too expensive. The only place I've ever seen EEPROMs used is in a lab.
We have various things that we're looking at.
That's the other reason they're expensive.
It's not showing all.
So, but those are the 6 types of ROMs. So we have 6 types of ROMs we covered there.
Right here.
Now we're going to go into the RAM, and that'll probably wrap today. I've got to stop at the same place I did last hour. So RAM is called volatile memory or read-write memory.
Let's go back to the real.
I don't know where this guy gets this RAM. I've never seen it done there. I just see R/W memory. Right there, read-write memory.
This happens to be just a website.
So ROM is memory that you typically only read.
As we look at our memory,
as we just talked about, flash ROM, we read-write to it all the time. So the definition between ROM and RAM gets very fuzzy at times when we get into the flash electronically erasable, because we are reading and writing from it, but it's non-volatile. When you take the power off, what's stored in a ROM is kept there. If you take the power off
the most common
of a RAM chip,
today
the contents is lost.
The DDR3.
Right there. So really the key thing there is not the read-write as much anymore. It's the volatile versus non-volatile.
DDR4
that's the key difference. Because ROM
2 months ago,
is also read-write today.
Relatively new.
See, that's where things get, and that's what makes this kind of a confusing discussion, is that ROM today is read-writable.
When you buy a motherboard,
and both of them are random access. RAM stands for random access. They're both random access.
Things you got to look at.
Random access means that
if we look at
that any location in memory,
for example,
right there, I can get to by just putting the address of that location and reading its contents.
Other things, we got the manufacturer.
Before random access, we had something called sequential access. The sequential access was a tape.
So, all of these things
where you had to play the tape and read this, then read this, then read this, and read this, and read this. It's been a long time since I've seen tapes used on computer systems. Anybody ever watch those old movies where they got the big computers that stand about 6 feet tall with the big tapes that go back and forth? Tape drives, that there? Yeah,
4 gigabytes are very common.
Yeah, it's been a while since you don't see those anymore. computers don't have those big tapes.
One
of my first computers that I had a Commodore VIC-20, and you actually use a little cassette tape recorder to save your programs on. That there. You would write a program in BASIC, and then you'd save it to the tape. And then you'd have to write down on a piece of paper where your programs were on the tape.
Should bring up
that there, so you knew where to find them. That there. So it wasn't exactly an easy, user-friendly way of doing it. The original IBM or the original Apple II, or the original Apple did not have a disk drive with it. It had a tape drive.
But
the Apple II had the disk.
The most common one you see.
The original Apple had the tape drive.
As you look at this right here.
So a lot of these very old computers use tapes.
4 gigs.
So those were sequential access memory.
Picked from.
So that's where the term RAM and sequential memory came from. Sequential memory doesn't exist anymore.
There, and you can go all the way up to.
There. So the term RAM should be replaced with non-volatile. Or volatile memory and non-volatile memory. There's 3 basic types.
Installed memory
there,
not available.
And this also is confusing. Is that one of the 3 types we just said is RAM is also called volatile memory. One of the types of RAM is non-volatile RAM, which sounds very much like a ROM.
As it turns out,
and what it really is it's RAM that's got battery backup. The most common two you're going to see are static and dynamic. Static,
yeah, these computers are old enough.
RAM uses flip-flops.
32-bit operating systems. When you talk about computers,
like basic digital class, you covered JK, D flip-flops, SR flip-flops. So you set and clear a memory location. Each flip-flop requires 6 to 4 transistor cells, right there, which means the static RAM is very large in size because every bit requires 4 transistors. If it's in high capacity,
these all have Windows 7. And Windows 7.
So it's very, very expensive.
2 generations
but it's high speed, very fast.
Windows 10 is out now. They skipped 9 for some
You don't have to refresh it. It's got some huge advantages.
That way, because
non-volatile adds
iOS
plus non-volatile is made up of. It uses extremely power efficient static RAM built out of CMOS, and it has a lithium battery as a backup. Non-volatile RAM is not really non-volatile. If that battery goes dead, the contents is lost.
All these parameters have to fit right there.
So it is
still
RAM. It's just that it's very low power
and what I discovered is my old memory was 1.5 volts, and the new motherboard can only support 1.2.
I'm going to skip this discussion on.
So I had to buy new memory
check sums.
So my upgrade doubled in price.
Then the last type of memory we've got that I'm going to talk about tonight is dynamic RAM. It uses a capacitor to store the information.
This memory here,
but because it's using a capacitor, we have to constantly read it and rewrite to it again. We have to go through a refresh cycle. So we have to, so it has to be refreshed periodically due to the fact it loses its charge. While it's being refreshed, you can't access it. So we have to have, every so often, we have to go through it and rewrite to the RAM. And that takes up time. So,
all right, this one has got 4 chips.
But again, one of the other issues you've got is
4 chips
you have a large number of cells. You run out of pins. I'm not going to get into that. He's talking about 64K. Anymore, we're talking 64. 1 terabyte by 1.
Right here. So there's 4 chips.
DRAM is almost always going to be in 1 bit or 2 bit increments. Static RAM is by 8, and ROMs are by 8.
Other memory devices that they
basically, when we look at DRAM, it's going to be some value. I'm going to say like 1 gig by 1 or 1 gig by 2, something like that. SRAM and ROMs, all ROMs, are going to be 16 gig by 8, for example, right there. So they're almost always going to be 8-bit wide, where the DRAMs are going to be 1 bit wide, right there.
It's got 8 chips on it.
So
you can see there's 4 chips.
Internally, it's divided into a square of rows and columns.
So this,
right there.
This is going to be here.
I'm not going to go through the setup of that there, where you go through and you strobe and right to that there. That's there. I'm going to kind of skip over that.
2 gigabyte chips. So these are 2 gig by 1.
ROM, we know all of them have 8 bits for data.
See, there's 4 chips here,
not the case for DRAM, which can have any of the 1 by 1 by 4 by 8 by 16 organization.
1 bit.
Typically, the chips are going to be by 1 or 2.
So again, as we go back here,
CPU. Also, you're going to have a chip select. We'll talk about the chip select tomorrow.
That had 2 bits.
Right there.
So that's it.
And the controls. I think it's pretty much where I broke things up last time.
Access time.
I should point out the other thing that I brought up was that when we look at a computer system, we have all 3 types of memory.
When you buy a new motherboard,
we look at a desktop computer.
List of approved memory devices.
We've got a CPU that's going to have, inside the CPU, it's going to have some memory, cache memory.
Some examples here.
Has really fast access. That's going to be static RAM.
It's got 12 address lines
the CPU.
and 4 data pins.
Some motherboards have some static RAM on the motherboard. Most don't.
12 address lines.
Then we also have our ROM, which is our BIOS.
Means it's
and those instructions are what tells the processor, or tells the system to go out and read the hard drive, look at the operating system, also configures it. This is normally called the BIOS, the basic input BIOS.
Times 4.
BIOS.
So this happens
basic
to be a 16K device.
Input, output system.
The one we had a few minutes ago was also 16K.
That's the BIOS.
That was
there. A lot of times if you have a computer system and the motherboard is having problems, the manufacturer will go back and update the BIOS and fix the bugs.
So it makes a difference.
Sometimes they'll update the BIOS to use different types of drives, whatever. So that's all going to be in the ROM. And then all the memory that you add to it, your 8 gigabytes of RAM is going to be DRAM.
Here it says that this is a...
So you see all 3 types of memory
512K chip.
System.
So there's 512 bits.
And with that, I'm going to...
And it has 8 pins for data.
Is there something about today? Because the last class seemed like they were all distracted. I look around and people are kind of not with it.
Well, the organization is going to be 512
boring
divided
subject.
by 8.
That's it. There. Oh, I can't tell how long this class was because this is tape.
K. It should be 512K. Right there, 512. 512K divided by 8, 64K. So it's 64K. My pen is not writing now. Okay, 64K by 8 is what is the organization. The number of address lines is, you just kind of go through this table, it's going to have 16 address lines right there. And this particular table, I started a table, let me just do it this way here, do another right there. If you've got 2 to the X, number of address lines, if you start with X and you say you start with 10, and I'm just starting with 2 to the 10th. Is 1K. And remember, locations, memory locations. So that's 1K. 11 lines will give you 2K. 12 lines will give you 4K. That doesn't look right. That does not look right. 2 raised to the 10th. There's 1K, yeah. Yep. 4K. 13 lines is 8K. Yeah, that is right. Yeah, that's right. Yeah. 14 is 16K. Every time I add a line, I double the amount of locations. 15 is 32K. 16 is 64K right there. So that's our answer, because our configuration was, we said was 64K by 8, so it requires 16 address lines right there. So 2 very possible questions right there on memory configuration. Okay, now I got a lot to talk about on this slide here. Let me erase all my notes here. Right there. Actually, I'm not going to talk to this slide very often, very long, because the following slides covers everything here. So, all right. There are 6 types of ROMs. ROM is a type of memory that does not lose its power when you turn it off. It's also called non-volatile ROM or read-only ROM right there. You can't write to it generally. Now, some of different types we can write to it right there. In particular, the flash EEPROM we can write to typically right there. But it doesn't lose power. The others, we normally don't write to it very often right there. So we've got the PROM, which is programmable read-only memory. We've got the EEPROM, which is erasable programmable read-only memory. The EEPROM, which is electrically erasable read-only memory. The flash PROM, EEPROM, which means we can erase it and reprogram it much, much faster. That's where it's called flash. And the mass ROM, which is manufactured with the ROM contents on it right there. So a PROM refers to the type of ROM that you can burn information into. They're also called one-time programmable. One-time programmable. You program them one time, and if you made a mistake, you throw it away. Right there. So, but you have a PROM program burner, or we call them burners, because the way that you typically program a PROM is that there's fuses in the PROM. It's, we've got a row and a column, and we've got a fuse in between here, and we go through and we blow the fuses. We burn the fuses, blow those fuses, so that it no longer conducts electricity right there. So we have a special piece of equipment called a PROM programmer right there. We also have the EEPROM. Now the EEPROM is a very, very seldom used device anymore. Matter of fact, I don't think I've seen one in probably 10 years, 15 years. That they're relatively old. This particular book talks about them because this is an older book right there, and all the textbooks are there. But I quite often will talk about the 2016 picture. I want to have a picture of one right there. Right there. Those girls don't look like they're part of 2716, but that's not really a very good picture. But what you see there is there's a little window here, and this is the actual IC. And I actually like this picture because you can see these are the wires that goes to the pins on the IC. This is the actual chip, and these are the wires that go to the pins. And they're bonded to the IC there. But what you do is, the reason you have the window on this is you put it underneath an ultraviolet light to erase it right there. And you put it underneath the eraser for like 20 minutes or so, and then you can take it out and put it back into the programmer and reprogram it. And then if your code's not right, you take it out and reprogram it again. When I was a student, this is the way we did most of our projects. So obviously, every time we made a mistake was at least a 30, 40-minute wraparound. You've gone through here, we've done one or two labs, and you saw how quickly we program these chips and change our code and reprogram them again, right? Just imagine if you had to wait 30 minutes between each time you did that. Some of the labs we did would have taken at least 4 or 5 hours. That's there. So we spent a lot more time in labs and debugging. And we did a lot more work up front to make sure we had it working right the first time, too. That's there. So let me do a 2064 picture. I think that's what I had before. Yeah, this is the one. Oh. And again, you can see this one here. It's the same basic concept, but here you can see the actual IC here, the size of that there. You know, when you look at an IC, the actual silicon is much, much smaller than the packaging. So that's one of the reasons I like these pictures here. Again, you can see the relative size of the actual silicon right here versus the ceramic packaging here. And these, by the way, these EPROMs were very, very expensive because you couldn't make them out of plastic. They had to be made out of ceramic because of the window. You know, most ICs are made out of plastic, which is very, very cheap, the packaging. But here, the cost of having the ceramic packaging and putting this glass window on there really made these devices very expensive, right there. So, and this is a very common looking EPROM programmer right there. You can see the little zip socket, you put it in there, and this is tied to a computer to program it right there. So, right there. So, yeah, they're all about the same. These are 24 pin. Okay. That's it. So, but again, they're not used, you don't see them very often because they were so expensive because of that window out there. And they were replaced by, and we'll skip through this step right here. Out there, the major disadvantage was that out there, this is a huge disadvantage right there. Right here is this one right there is that the EPROM UV you cannot reprogram in the system board. Since you had to erase it, you had to take it out of the system, erase it, put it in the programmer, and then put it back into the circuit. So it was not a very friendly way of programming microprocessors. And but incidentally, one of the 8051, there was an 8751 which was an erasable 8051. That's there. And we would do our 8051 labs. We would program the 8051 and take it out of the programmer and put it into the circuit, test it. If it didn't work right, we took it out of the circuit, put it back into the eraser. That's there. So you could see the amount of time you spent erasing and reprogramming these devices. Not very friendly right there. So, and there is a pattern and number. 27128 refers to 128K bits in EPROMs are all by 8 and an access time of 250 nanoseconds right there. Well, the EPROM was replaced by the double EPROM, sometimes written E squared PROM right there. Sometimes you'll see it written as E squared PROM up there. And what it allowed you to do is erase it electronically. And one of the big advantages of that is that since we can erase it electronically, we could design into our system board the circuitry to program it, and therefore we can reprogram it in the system. And that's a huge advantage, because, for example, our boards we've got, we could design a circuit, we can put the pins in there to connect it to a programmer there onto the board itself and reprogram it in the system. So we didn't have, when we're debugging the software, after we've already built the hardware, we don't have to remove the chip. And this is extremely important because if you look at our chip, it's a surface mount chip. It's not a socketed chip. That's there. Most of the Silicon Labs chips are not socketed. That there are a lot. Matter of fact, most microcontrollers today are not socketed. They're surface mount. There, and being surface mount means that unsoldering and resoldering is not a trivial matter. That's there. So there are some sockets for them, but that there. So the E squared PROM was replaced that there, and this is what's used in most microcontrollers that there, and most desktop or most motherboards and that have ROMs on them. There is the double E right there. The next one is the flash, which programs much faster, and that really isn't used much for PROMs as it is for memory. It's replaced a lot of the hard drives in particular. Your thumb drives, has anybody seen a computer with a floppy disk drive on it in the last 5 years? Anybody ever seen a floppy disk? Not there. You've seen floppy disks up there. Well, I mean, the floppy disk was replaced by the thumb drive, essentially. That's there. And the thumb drive uses flash EEPROM is what it uses, the thumb drive. That's there. There. And that's what, and the other place commonly used that there is that they make a comment here on the next slide here that there I'll get to it. Major differences is that between each square here is the flash memory contents are erased but there some are done by block, which is the most common way done now. That there. So you can erase that there on the flash that there. Where a EEPROM, you erase the entire thing and then reprogram it. That there. Here we can do it block by block or section by section, which makes it much more usable for that there. You can tell that this is a little bit dated here. It is believed that the flash memory will replace part of the hard disk as mass storage medium. That is already starting. That is definitely becoming reality. That there. Has anybody heard of solid state drives? SSDs? An SSD is a solid state drive. It replaces a standard hard drive in a system. You can look at, for example, going back to my favorite place here, and SSD drive right there. And here is a MSATA right here. This is what I've got in one of my systems right there. This is a very expensive drive right there. This is a 1 terabyte solid state drive right there. And this particular drive is kind of hard to show how big it is on this slide here, but that's there. But it's about this. I'd say about what is that? About 3 centimeters, maybe by 10 centimeters. Do they have the size listed here? Specifications. They probably don't. They're standard sizes. All right. 5 millimeters or 50 millimeters by 20. So you're looking at about 3 centimeters by 5 centimeters. That's not very big, is it? Right there. And this just plugs into what they call an M.2 socket on the motherboard, and then it screws into the top there, and that just mounts to the motherboard right there. So, example, let's gigabyte Z170 DDR3. Take the dash out of there. Well, let's just go Z170. Okay, all right, this one here might. And that picture that Trying to get one where I can. My battery's about ready to go dead here, so. All right, it's a little hard to see. Wait for this picture to clear up here a little bit. Hopefully it clears up. If I can find it here. Yeah, right here it is. Okay, if you look at this picture here, you can see there's the socket right there. And yeah, as soon as I do that, right here. As you look at this right here, you can see next to that box, let's just stand up over here. If you look at this picture here, this is where that's where the solid state drive plugs into, and then it screws in the top there at the top, right there. And that's, you can put up to a 2 terabyte hard drive, and it mounts to the motherboard right there. So that is now replacing a lot of the system drives. They're still quite expensive, as we saw. If we look here at the M.2 SSD right there. Yeah, I see